I'm going to see what happens if I try to put this. Do you see it full screen now?
Yes, yes, perfect.
Okay. Is it now, if I change this to presenter mode, do you see presenter mode or do you see presenter mode?
We still see the full screen now.
Oh, excellent. All right.
That's what you want.
The tech works. All right. Excellent.
Yeah, I think I wonder if there is actually something like a market cap or a GDP for all the renewable industries, kind of following Professor French's talk, just to see how it's changing year by year. Because I mean, I recently saw the crypto market, like Bitcoin, went from like $3 trillion to less than 1 trillion. So trillion, you know, is not so difficult, I think, as long as, you know, we sort of organize. Anyway.
And I agree, Drew, but getting it to 10x and another 10x is what we need. And that just takes time. Things slow down. The bigger you get, the harder it is to get that next, 10 gigawatts of capacity, et cetera. So that's why I'm concerned about the time scale here, because it's a big lift for a long time, and we've got to stay focused. As Professor French says, it's a collective action problem, not just within countries, but between countries. And we need all the technical options we can throw at it.
Absolutely. And I think Yet will bring that. So let's get started. I'd like to introduce my dear colleague, Professor Ming Chiang, who actually needs not much introduction to this community. Professor Chen is the Kyocera Professor of Material Science Engineering at MIT and a member of National Academy of Engineering. Yet's research aims to design, synthesize, and characterize advanced materials and devices for use in clean energy technologies, including low-carbon transportation and grid-scale electrical energy storage. His group studies electrochemical processes for the decarbonization of industrial materials and the mining, separation, and recovery of elements from various feedstocks. Current projects focus on novel conduction mechanism in solid electrolytes, metal electrode-based solid-state batteries, batteries for electric aviation, grid-scale storage batteries, decarbonization of cement production, and electrochemical mining of ashes and other waste. So Yet, you have the floor.
Thank you, Ju. It's a great pleasure to be here and to see so many people joining. I'd like to talk today about this a nexus, I'll call it, between renewable energy, materials production, and mining and waste disposal, and really to emphasize some of the issues that we need to be aware of when we think about scalability. This is work that I've been first started to get focused on maybe about 5 years ago. And I've learned a lot in the process about large-scale materials and large-scale processes. And what I'd like to do is to give you sort of 3 vignettes, 3 short stories, and to illustrate what it is that comes into consideration. And so actually the first one, I'm going to talk a little bit about large-scale energy storage. And so the problem in decarbonizing the electricity system that we face, if you look at this chart, what we see is that there's a projection that renewable solar and wind will continue to increase, and more so than anything else. And even though this plot doesn't show nuclear increasing, I'm hopeful that we'll see that take place. But the issue is this base load. And as it says here, there's about 780 gigawatts of and mostly natural gas power plants. Coal's going to go away. Right? And this is the decarbonization challenge that we face. Recently, you read and hear about long duration storage. And I kind of wanted to put a number on that. long duration storage today, to me, means multiple days. For a variety of reasons, it doesn't really mean seasons. I don't think we can get to cost-effective seasonal storage with what we have at hand today, with the tools that we have. But this chart shows every day of the year in Texas in 2021. And if you look closely at the points where you have a gap between the line, which is demand, and supply, which is everything below it in the blue and orange, you see that the gaps that you're trying to bridge are on the order of several days. Right? And so just to pick a nice round number, I'm going to call that 100 hours or 4 days. Right? And the issue with bridging those gaps with storage is that it has to be very low cost. And there are a lot of ways of showing why or how low cost it has to be. But this is what I found to be really the simplest way of explaining the problem. It's a three-term equation. On the left-hand side is the cost that we're competing with. So natural gas today, $2,000 a kilowatt to generate electricity. Right? Now, on the right-hand side, if you take what I just showed you and say that we need to store electricity and over about a 4-day period, 100 hours, well, a simple arithmetic tells you that the cost of the storage has to be $20 a kilowatt hour. And immediately you see the gap. Lithium ion, by the time you've taken a lithium ion pack and made it suitable for the grid and interconnected, it's about 250 kilowatt hour. Okay? And so this is the cost gap. And we have been using a chart for a number of years now to look at what the cost entitlement is of battery chemistries. I don't include on here the materials that Mike Aziz will talk about tomorrow, which I'm very interested in getting the update on. But here, what we see that is on this chart, which is the cost of just the materials that store the energy, plus the electrolyte, that in order to get below $20 a kilowatt hour just for the materials, you really need to look at the most abundant materials we have available. And as it says here, using air as one of the electrodes is great because air is still free. Okay? And using a low-cost inorganic, sulfur or a metal like iron or zinc for the other is a way to get the cost entitlement way down to the point that by the time you're done with the system, you can imagine getting to $20 a kilowatt hour or less. Right? So that's one part of the problem, is the cost problem. The second part of the problem is the scalability problem. And so one way that we can benchmark the scalability that we need is to try to project how much storage we might need to fully decarbonize an electricity system by 2050. And so there are a variety of ways of estimating this, but I'm going to give you a nice round number of 100 terawatt hours and ask you to just hold that in your mind. For instance, there's a McKinsey report recently that brackets that, and it goes from 80 to 150. So we'll call it 100 terawatt hours for approximate scale. And let's say that we want to do this by mid-century, right? So let me illustrate the scalability problem here with lithium. So for lithium ion, the question that's often asked is, do we have enough lithium? And so I want to kind of flip that question around and say, actually, it's not, do we have enough lithium? Because on this plot, the vertical axis is a compound annual growth rate of the production of lithium, right? And on the horizontal axis is the total deployment by 2050. And this plot is due to Elsa Olivetti and Bob Jaffe. It's in a recent report, a study from the MIT Energy Initiative called The Future of Energy Storage, which you can get online. Right? So you see a vertical line for our target of 100 terawatt hours. And then you see that the resource limit is to the right of that. So the question is not, is there enough lithium? It's how much do we have to scale the production of lithium? The curves here, the blue and red and green, represent how much of the lithium we mine actually goes towards batteries. And so let's just pick the 100%. So let's say that all additional lithium we mine from this point on goes towards batteries. The intersection of the blue curve and the red line, you can read off the left axis. It says that for the next 28 years, we need to increase the production of lithium at a 10% per year rate. That's the compound annual growth rate. Now, that turns out to be a very, very heavy lift because the histogram on the far left, shows the last 18 years of production in terms of the compound annual growth rate in any one year. And so what this tells us is that we have to produce at the maximum historical compound annual growth rate for the next 28 years to supply the amount of lithium-ion batteries, if that's the technology we choose. Right? So this illustrates the scaling problem. Another part of the scaling problem is actually the production of the batteries themselves. It's no secret that the cost of lithium-ion has come down massively over the 30 years since it reached the commercial marketplace. Right? On the right-hand side here is a plot of the production of lithium-ion. So this is not the lithium or other elements, which I just showed you, but the cells themselves. And over the current decade, 2020 to 2030, it's projected to increase at a compound annual growth rate of about 20%. However, at the end of that decade, we'll be at a number of 2.5 terawatt hours per year. And so that's 2.5 terawatt hours per year compared to the 100 that we need by 2050. So, in essence, we would have to keep up this compound annual growth rate of 20% for the next 28 years as well. Right? All this, cries out for both a lower cost, more scalable storage solution. And so I and many colleagues at a company called Form Energy in Somerville, Massachusetts, have been developing a battery called, which is known as the iron air battery. We didn't invent the iron air battery. We're simply developing it for this particular purpose of multi-day energy storage. And an iron air battery, I won't go into details here. They're available in the literature. Basically, it discharges by oxidizing iron. That's energetically downhill, going towards the ground state. And it charges by reducing that iron back to iron metal. Right? So this can be an exceptionally low-cost battery. We have an existing iron supply chain. There's iron produced on essentially every continent in the world. And if you start and you look at this iron supply chain and you go from iron ore to high-value forms of iron, what you find is that there's a point at which in this supply chain called direct reduced iron, which is the lowest cost metallized form. Right? And so it makes sense to grab this form, DRI. It comes in the form of marbles. Right? They actually look like this. This is a 55-gallon drum full of iron marbles. And so if you take these iron marbles and produce a iron air module, well, this is a pathway to very low-cost energy storage. This module on the right that you see here stands about 4 feet tall, about 4 feet wide, and about a foot thick. And so this is an iron air battery that uses this form of direct reduced iron. Okay, why is this so scalable? Well, it turns out that compared to the example I gave you for lithium, if you look at iron production today, and to just explain the production scenario, there are iron plants which are distinct from steel plants. The iron plants exist today primarily to supply this feedstock called DRI for electric arc furnaces, an electrified form of iron production, which is lower carbon than the blast furnace that historically was used. But if we just look at the scaling here, one of these plants, and this is one in Convent, Louisiana, a Nucor plant. The left image here, you see these what look like mounds in front of the shaft furnace. Those are actually all mounds of iron ore pellets waiting their turn to be reduced to DRI through that shaft furnace. So it turns out that to reach that 100 terawatt hour target, just over 10 years, would require less than a 2% increase in global iron production. Right? And so this is an example of scalability where if you look closely at what is required of the mineral resource for lithium ion, you come to the conclusion that it cannot do multi-day storage. right? It's still great for a whole bunch of other applications, such as electric vehicles and for short duration energy storage, but the multi-day storage problem requires a different solution. So here's a nexus between iron production and long duration storage. And in fact, this leads me to my sort of second topic, which I'll talk about in a second, which is, ways of decarbonizing steel production as one example of the commodity materials that we need to decarbonize. Okay. Just to close on this part of the story, Form is, as I mentioned, in Somerville, Massachusetts, and the West Coast, and Pittsburgh, and soon somewhere in the middle of the country for their first production plant, which will be on a riverway, because you have to ship in that iron. It's an exciting development, and as you see here, we're hiring, right? So if you're interested in this problem, please go to the Form Energy website, and there may be a job that is suitable for you to apply to. Okay. I'm going to now transition to the second part. So that is a backdrop of an example where scalable materials production is critical. What we have recently started at MIT is a project called, we actually have a new center called the Center for Electrification and Decarbonization of Industry. It's part of the MIT Climate Grand Challenges. And after about an 18-month down selection process, there were 5 flagship projects selected and funded at MIT under Climate Grand Challenges. And this is one of the 5. And it's the one that is the most focused on industrial production. Right? So the rationale for this new center is that it turns out that there are 4 greenhouse gas emitters which are far and away the largest emitters in the world. They're cement, steel, ethylene, and ammonia. Right? And so decarbonizing industrial production requires that we tackle these 4, and we selected these as the targets. Right? A more granular image of where the emissions comes from, you can find in this paper. You can see the reference down in the lower left. And there's not a complete agreement as to which one is the greatest, but there is general agreement that these are the top 4. And so just these 4 together are 45% of all industrial emissions. Right? There's a cascade of others below it, right? And then that is equivalent to 15% of global emissions. Right? And so, for example, I'll just point out here, aluminum is number 5. Aluminum is already electrified, right? But it's a significant emitter because it still uses a carbon electrode, and therefore that is, at least aside from electricity, is one of the sources of CO2 emissions, right? But we chose to tackle these 4, and I'm going to leave the steel description of the steel effort to a future talk from my colleague Antoine Alenor, and the ammonia and ethylene to my co-director at the center, Bilge Yildiz, and others who we'll talk about in the future. I'm going to spend my time talking about cement, which is something I've been learning about over the last few years. So just very quickly, just to level set all of us, when we talk about cement, cement is not concrete. Concrete is the aggregate or gravel or rock and sand that's now bound together by the cement, which is the paste in between. And actually only about 10% of that concrete is cement. Right? But still, even though it's only 10% of the concrete we make, the cement we produce is some 8% of global CO2, 4 billion tons a year. And a really easy number to remember is that 1 ton of Portland cement made today produces about 1 ton, slightly less, 0.93, but about 1 ton of CO2. Right? And the CO2 in this cement comes from 2 particular sources. One is the calcium carbonate or limestone that we use, which is a chemical source of CO2. And that's about 50% of the CO2 emitted. And then the rest is from the fossil fuels that we burn, which today is still primarily coal. And so if we're going to decarbonize cement production, we really have to tackle both of these. And so I'm going to talk about how we might tackle both of those. Right? Okay, next slide. All right, let me just show you the problem of increasing urbanization. Right? This is a nice image to capture it. Here's Edith's house surrounded by new construction. Right? At global scale, what we have is the following. We project about 10 billion people on the planet in 2050. The rate of construction and the rate of production of cement, just the cement part of it, is the equivalent of one New York City every month, right, from now till about 2050. Right? You can read about it in Bill Gates' book, right? And the green premium, the cost today to decarbonize cement, if you use post-combustion capture, point source capture out of the flue stack, out of the flue gas, right? That roughly doubles the price of cement today. And I just want to point out that for all of the cement majors, that is the current, plan of record to decarbonize through carbon capture. Right? So we started to look at a different way to do this, which is to electrify it. And the inspiration came from the following observation. So, electrolysis, electrolyzers are not only used to produce gases. Most people think of them as being used to produce gases. For instance, here, this is a H cell that's a simple, neutral water electrolyzer. But what the color indicator shows you is that, electrolyzers are also used to produce acids and bases. And so the high pH side on the right is where we have hydrogen evolution, and the low pH side is where we have oxygen evolution. So this is a simple lab, just a lab demonstration. And it turns out that with the availability of both acid and base, we can do a lot of materials processing. And that's the point of what I'm going to be talking about here. At industrial scale, it doesn't look like that, of course. Right? I just want to show you an image of an industrial scale chlor-alkali electrolyzer. So chlor-alkali electrolyzers are primarily used to produce chlorine and base, but because it also produces hydrogen at the same time as chlorine, so you can see here chlorine gas and hydrogen gas coming out of this electrolyzer. You can recombine the hydrogen and chlorine to make HCl, and because you feed this device with a salt solution, NaCl solution, you therefore produce hydrochloric acid and sodium hydroxide, the acid and the base. Okay? Now, what could you do if you had both of these? Right? So the idea we conceived was that we could use the acid to decompose the metal carbonate. And virtually all metal carbonates in acid will decompose and release CO2. And it'll do so at ambient temperature. This is the vinegar and baking soda trick. Right? And so that produces pure cold CO2, which you could capture. It's already captured, rather, which you could sequester more easily than hot flue gas CO2. So in this scenario, what we do is that we dissolve the limestone in an acid. Right? And we first did it with nitric acid, but HCl works just as well. And the dissolved calcium can then be precipitated to calcium hydroxide using the base side of the electrolyzer. Okay, so how does this all end up? It turns out that, oops, let me page down one. It turns out that if you use this to produce calcium hydroxide, which is what you see on the left-hand side here, that calcium hydroxide can then be reacted with silica to produce a compound, a tricalcium silicate known as alite. Okay? And this is the desired phase in Portland cement. And I'll say just a little bit more about that in a second. Okay? So here's a process where at the upper right, you see that you can take natural limestone and produce a pure hydrated lime for cement production. And at the same time, it actually purifies the material because there are a lot of things that are not soluble in that acid stream. Right? And so this now suggests that this can also be a mining and purification process, which is going to be the third thing I talk about today. Right? But let me talk a little bit more about this alite compound. So cement is a fascinating material. This chart shows you what happens to cement, which is the mix of materials we have on the far left here, right? By volume. The vertical scale is volume. The horizontal scale is time, hours on a log scale. And the source for this plot you can see at the lower left here. And I've annotated it a little bit just to highlight the gray phase halide here. That's the tricalcium silicate. Okay. And so as you watch the evolution, the reason the volume increases of the solids is because it's hydrating. Okay. As the aqueous solution is producing solids that are hydrates. What you see is that as the halide phase, that gray band disappears, the predominant new phase that appears is calcium silicate hydrate, or CSH. Okay. This is the binder phase in cement that is the glue that holds everything together. And what you see is that there's actually an excess of calcium hydroxide produced in this process. But most of the calcium is used to produce the CSH. So an interesting part of this compound halide, tricalcium silicate, is that if we look at the calcium silica phase diagram, the red circle here is the halide phase, tricalcium silicate. And what you notice is that, well, there's a eutectoid here. It turns out that that phase is only stable above 1250 degrees C. Right? This is the reason that Portland cement production today is a high temperature process. It was discovered in 1824 that this tricalcium silicate is the fast reacting silicate, excluding sodium silicates. Now, sodium silicates are water soluble, but high sodium, or high alkalinity in a cement is not the same cement. It's actually a different kind of cement that may have some uses, but is not widely used. It's not Portland cement. So aside from sodium silicates, this calcium silicate, the halide phase, is considered the most cementitious phase because it's the fastest to dissolve and the fastest to react to form calcium silicate hydrate. And so this I'm showing you to highlight the second part of the problem, which is, how might one get around these thermal processes, right? Can we make the equivalent of tricalcium silicate halide fast reacting at ambient temperature without needing to go to these high temperatures? So, since we originally, since we published that paper in PNAS on this electrochemical approach, there's been a commercialization effort underway, and this is a company called Sublime Systems, which is about a little over 20 people, also based in Somerville, Massachusetts. And you see here also we're hiring, right? So if you're interested in this problem, please visit our website. And so this is now at a stage where there is a scale up to pilot scale of this electrochemical process for producing calcium hydroxide. And the cement that's being produced, I can't tell you the details today, but is actually produced entirely at ambient temperature and produces a pretty good cement that has, is showing all the properties that we believe will eventually meet, form fit function for Portland cement. And we've gone so far as to produce some, what you see is the MIT mascot in a decarbonized cement beaver here. Right? And so this is a direction for using electrification to decarbonize cement. What we had, envisioned at the outset is that there might be this ecosystem here where we take limestone and decarbonize it through electrolytically produced reagents and use those reagents to produce the input into cement production. Now, I will admit that what to do with that nice, clean, pure CO2 is still an issue. And, there is not yet a proven CCU, CO2 upgrading scheme that is at scale. And so any way that you sequester it is a cost adder, which is undesirable. And so that's a part of the process I think that we still need to think harder about, okay? So this is the second part of the second story. And I'm going to just close with one last story and hopefully leave some time for discussion here. This is a spin-off of the idea of using electrolytically produced acids and bases for materials processing. And it's a problem that has to do with trash. And in this case, I want to highlight in particular Mike Wang and Duhan Zhang, who have really been the leaders of this RPE project, where we collaborate with Venkat Vishwanathan's group at CMU, and my collaborator at MIT is Elsa Olivetti. And so let's talk about trash, right? Okay, the plot here on the left is an interesting one. The blue curve here is the per capita generation of trash per person, this is per capita in the US by year. And the good news is that it's been flat. So we don't generate more trash per person than we did in almost 20 years ago. The bad news is that our population is increasing, and so the red is the total, right? And so we have this escalating trash production, and about 50% of that trash that is collected goes into landfill, which has issues that you see here, right? And so one of the industrial operations that deals with that trash so that you don't have to landfill so much of it is a waste to energy plant. This is an incinerator. We know it is an incinerator, right? So trash comes in, and it's a fuel that's burned in order to generate electric power. And out of it comes an ash. And that ash is now reduced in volume from the solid waste by almost 90%, which makes it a more easily landfilled material. Right? Okay, so let me describe the basic value proposition for how one of these facilities works. This is one example, an EcoMain facility. We have the data for 2019. So 177 kilotons of trash come in. Produces 109 gigawatt hours of electricity, produces 43 kilotons of ash. And so what happens to the output of those two? Well, the electricity was sold for $4.4 million, right? We're here, they're at an average selling price of 5 cents a kilowatt hour. The ash is landfill, but it turns out that you have to pay the landfill at about $50 a ton. And so you see that the offset here is that there's a negative cost of about 2 million, positive cost about 4.4 million. And so per kilogram of ash produced, so we're going to normalize things to per kilogram because that's going to help us think about the value of materials. It costs about 5.5 cents per kilogram of ash that we produce here. Okay, now if we keep in mind that that trash is mostly consumer goods that we've already paid a penalty in energy and everything else that have produced, it wouldn't surprise you that there's some value in that ash, right? And so this is a chart of the elemental content just in a decreasing concentration on a log scale, right? So the inset image there, this is what this ash looks like. It can be black, it can have carbon in it, it can be sort of brown or somewhat gray. And so silica, there's more silica than anything else. And here's iron, right? But as you see this cascade come down, you see that the world over, if we blow this up to a linear scale, there are wide variations in the elemental content. But on a log scale, you see that these are the ashes for 7 different sources, 7 different analyses. So the interesting part of this was that if you take those analyses and now turn it into dollars per ton or dollars per kilogram value by element, horizontal axis is by element, and the horizontal line here is my electricity value of 5.5 cents. Right? What you see is that there's value in that ash, which is well in excess of the electricity value that's obtained today. Right? And so the value proposition that we therefore wondered about goes like this in this flow chart. If we were to use the electricity from a incinerator, instead of selling that electricity at value that's declining because electricity price is declining, if we were to use that electricity instead to power a process that electrolytically produce acid and base and use that to mine the ash for the elements that all the elements that of value, how would this work out? Right? Could we, number one, do it technically? Number two, does it make economic sense? Right? So we don't have the complete answer to the second question, but I'll tell you a little bit about the first one. So here's an example, 3 different sources of ash, and this is what they look like. And so I'll show you some experiments that take one particular fraction called sand out of a Yorktown facility in Pennsylvania. Right? And the way that we've mined this ash is to use two types of processes. First, we produce acid and base, or in this case, we're buying the acid, right, and the base. But in principle, it could be electrolytically produced. And we leach the acid, leach the ash for everything soluble. And then we carry out two processes. One is the electrochemical one. We electrodeposit or electrowin the metals. The second is a chemical process, which is that we precipitate in a pH sequence those elements that are hard to electrowin. Okay? So here's an example of the sequential electrowinning of, in this case, 3 different metals, which were the metals present in the highest concentration in our ash that could be electrowon: copper, lead, and zinc. Okay? And so what you see is that, as you go down the electrochemical series and, and systematically, vary potential, what you do is to sequentially separate out the metals. And so right now, at this point, we don't have great separation of iron and zinc, but, but the lead is pretty easy. Okay. What you have in electro-1, you can then precipitate with the base. Okay? And so this is actually an experiment where we didn't take out any of the electro-1 metals. We just precipitated everything. And the main point is, if you go first to the high pH, it's easy to separate out calcium that comes out of the highest pH. Everything else is already precipitated by then, if you're starting from low going to high. And before that, you can get the magnesium first. And then you have a group where you have a cluster of others that are going to take more work to separate, right? So you look at the purity of these, and this shows that, as you vary pH from 4, 9, 12, 14, the calcium, the magnesium are pretty pure. And now you have iron and aluminum and a few others mixed in there, right? So that requires some more precision than what we've used so far. And we believe that there are chemical engineering approaches that can start to parse those as well, right? Okay, so this analysis of what we technically can separate, okay, assuming we make it somewhat more selective than it is today, tells us that we can recover about 12 cents per kilogram of ash out of this one source, which otherwise would cost you about 5 cents a kilogram in order to landfill. Okay? And this is the sequence of, or the order of operations. Well, actually, this is not quite the order of operations. First you electrowin, and then you precipitate. Okay? And so what we've gotten so far in this is that we, technical economic analysis, we haven't, worked through all the CapEx and other things yet, but if we just look at the energy involved, right? The energy for electrolysis is on the left. SLR is the solids liquid ratio, and that's a strong variable, high sensitivity to how much ash and how much leachate. The horizontal axis is the concentration of the acid that we use, right? And then there's an electricity price involved here. And so the electricity cost should be well below the value of the ash. Value of the ash is the red line. And where we are currently experimentally is that red circle down the bottom. Okay, the other main consumption of energy goes towards electrowinning. That's on the right-hand side here. Right? And so here the horizontal lines, again, represent the value. And what it tells us is that, well, we need it's actually not very sensitive to the current efficiency of electrowinning, but we do need to have a sufficient current efficiency to get below those lines. And the upshot is that where we are today, which is relatively inefficient, there is enough electricity from the facility to power this entire process on paper. Right. So with increasing efficiency, we have a little bit left over, and I think we're going to need some left over for other ancillary processes associated with this. So, well, it could work, right? That's my main message about this process here. So I think, so with that, I'm finishing. I'm going to stop here, and this is my sort of the third example of ways to use electricity to produce chemical reagents for mining, materials processing, waste processing, cement production, and in the future, hopefully other things. Just a few days ago, the Department of Energy made this announcement, which actually caught me by surprise. I didn't know that this was coming. But this is developing into a thing, like decarbonization of American industry. Right? And so the EERE is going to be funding this. I believe the FOA is due out in third week of August. But when you go down this list, this includes a number of the things I've mentioned here: chemicals, iron and steel, cement, and concrete. Right? And so I hope I've given you kind of a flavor for what I think will be an important developing area of research that hopefully many of us can participate in. All right, with that, I'm going to stop sharing, and I'll be happy to answer questions.
Thank you, Yet. Let me first ask that in the generation of acid and base with electrical energy, you generate oxygen gas and hydrogen gas. So if we use it for cement production, I guess the volume will be pretty big. And also in the recovery of the municipal waste ashes, there's a whole range of products. So how do you think about distributing these products? For example, we need to match them with like a big hydrogen economy
Let me just answer the first question, which is, I gave that chlor-alkali process as an example. And I also, because, if we look at the way acids are produced today, sometimes they're the output of other chemical processes. But if you just want to produce acid, so sulfuric acid is one of the two lowest costs, and that's produced thermally, right, from sulfur, as SF2. Hydrochloric acid is produced electrochemically. That's why I gave that as an example. Right? But these electrolyzers, the chlor-alkali facilities, are designed around producing gaseous byproducts primarily, chlorine gas in particular. They are by no means the most efficient. Right? And so the volume question is not so much a volume question, because you can take that hydrogen and chlorine and react it right away back to HCl. It's done, you can do it through something called the acid burner, but it's very inefficient in the sense that you've boiled off two gases and now you're going to recombine two gases, and the recombination runs at 2000 centigrade. Right? You produce a lot of high-grade heat, but there's a lot of the high-grade heat isn't used today. Right? And so I think that even though these are our examples today, the leading commercial electrolyzers that produce acid and base are the chlor-alkali electrolyzer and the EDBM electrodialysis using bipolar membranes. That is used, for instance, for producing acid for your fruit juice and a few other things. Right? So this is how we do it today. I think that there are ways to produce acid and bases electrolytically much more efficiently if we keep in mind that our purpose is to do materials processing. Okay, so the second, your question about co-products. Yeah, so where do you send all that stuff, right? So you have a municipal incinerator, you have to distribute those. I think that one thing, I didn't say what happens to the silica that comes out of the ash after we've leached it. Turns out that acid leaching is a way to produce pretty high purity silica. Well, one use for that is cement. Right? And so in the urban environments where you have an incinerator facility, you also usually have a cement plant nearby. So that's a high volume thing that's one of the higher volume. And calcium, what do we do with the calcium? Right? I talked about calcium silicate as these are the key ingredients in the cement. But the other use of the calcium is that it can actually be fed right back into the incinerator. Right? And the reason is because there's some desulfurization going on, and hydrated lime is actually a consumable for municipal incinerators. So what I described here can actually be a loop, and most of that calcium can go right back in. Right? So that might help me with my supply chain issue. Right? But You know, the metals, yeah, we have to find places to send them off. So you know, that is something. The more valuable the metal, the easier that will be. Right? You know, I think it just in general, one of the potential advantages is that these are going to be in relatively urban environments where, you know, you can probably find ways to use your output.
Fantastic. So you're really talking about like a reconfiguration of the entire industry, the supply chain. I mean, it's a new vision for the economy, essentially.
Yeah, you know, in the United States, you know, incinerator is a really dirty word. If you go to, you know, for instance, some countries in Scandinavia, you know, they don't call them incinerators, but those same facilities are considered, you know, sort of model industrial plants. You know, they have, you know, playgrounds on site and things like that. People go to visit because they're interested. So I think we need to have a different view of what it, you know, what it takes to have that circular economy we want.
There's a question from the audience, Zishuai Zhang. I think he's asking about this high temperature clinker phase that you synthesize electrochemically. I guess it's maybe commercial secret, but anything you can talk about, like what's the science behind this process?
Yeah, you know, this is something that we just, it's both going on, you know, industrially, but we're also just getting started on this at MIT. But you know, so I can't say too much about it, but I will say that you know, one thing that I've learned. So I'm relatively new to cement. You know, cement is one of those fields where there are serious practitioners who, if they heard what I just said here, would be shaking their heads and saying, "Man, you know, you're not. There's so much you're missing." And yes, there's so much I'm missing. But I think what is true is that if you want to make cement, you need calcium silicate, right? And if you simplify it to the problem that what you need is calcium and silica that dissolves quickly, right? In high pH solution, if you can get it to dissolve, it will form CSH, calcium silicate hydrate. Right? And so if you just view it from that point of view, of that's what you need, you know, we need, you know, high aqueous solubility. I think there's a lot of interesting research to be done there on how to make that happen. Right?
Super interesting.
I'd like to ask a quick related question, too.
Go ahead. Time. Yes.
Yeah, Ming, a great bunch of innovation there. Enjoyed that thoroughly. Let me see if I understood something about the cement production. Do you have lower overall energy requirement because you're not having to go to high temperature? So, yeah. So how much is that? You know, 75% of what I do in a thermal process, or is it 5%?
Yeah.
What's the win there in terms of energy supply? Energy demand? You're right.
You know, people, you know, called us out on that. This, you know, electrolytically, how much energy does it take to decarbonize that limestone? And yeah, you know, I think that you really have to look at the process holistically. And you know, electrochemical processes are not always lower energy consumption, and you do need to have that electricity supply. So we do have to take that into account. But that really was, you know, so well, that, you know, that may not be enough. We better find a way to get rid of that thermal process as well. Okay. Yeah.
Yeah, Adam, I'll just speak up.
Can you hear me all right?
Yes.
Yeah. Hi, Adam.
Hello. Great. Very nice talk. Very interesting case studies. Seen a couple of them. I'm curious on the iron air battery. The entropy change in the charging reaction, I guess, seems like it could lead to a lot of energy loss. Can you talk about the efficiency or the round trip efficiency of that
oh yeah,
system?
Sure. Yeah, happy to talk about that. So I'm gonna begin with a quote from my co-founder and the CEO of Forum Energy, Matteo Jaramillo. He likes to say, you know, batteries are just like people. Everyone is deeply flawed in some way. It's just which flaws you're willing to live with. Right. So the history of iron air is that it was studied at various times in history, but at Westinghouse and other places, actually for traction batteries. And, I'll tell you, there are two sources of inefficiency, and it's important to be very transparent about this. So one is that anytime you have a oxygen reduction reaction, oxygen evolution reaction, those overpotentials lead to inefficiency. That's the positive electrode. Negative electrode, the iron, the oxidation and reduction potentials are so close to HER, it's generally impossible to avoid some HER. And so you have a coulombic loss at the negative electrode and a voltage loss at the positive. And so it's compared to lithium ion, which can be 95% plus efficient, this, is typically more like 50% round trip efficiency. And so you say, well, that's really terrible, right? And until you think about, thermal processes and fuel cells, the 40%, and solar cells at 20%. And so in the end, it techno-economically works because of the very low cost of electricity. Right? You would not do this for two ways you wouldn't use it. One is if you have such high round trip efficiency that the thermals are important. And so, yeah, if you were to charge and discharge at high rates, you have to get rid of the heat you produce. And in this case, multi-day storage, you can do it passively. You can, but the inefficiency is still there, right? And it's just that when you look at the entire problem you're trying to solve, they're storing and deliver electricity, and the key is at the end of the day, what is the cost of that electricity I deliver when to the customer? This turns out to be a pretty suitable solution.
Great, thanks very much, particularly at the like you said, the very low cost of solar electricity in the summer. So seasonal storage sounds like it makes a lot of sense.
Yeah, well, real seasonal storage is still a little bit beyond this, but I think that'll be super interesting. You may know this, but Antarctica, well, there's a great place to have seasonal storage. It's sunny for 6 months and dark for 6 months, but you have pretty good solar over 6 months of the year there. Right?
Yeah, so I think your estimate of 100 terawatt hour is probably still on the low end. Is that only for the US or is that for the whole globe?
Yeah, I'll tell you that is actually for the globe. And the way that I like to benchmark that is to say 2050, 10 billion people, 100 terawatt hours. The equivalence is that every 10 persons has a battery of 100 kilowatt hours, basically an EV battery, EV-sized battery, somewhere in the world supporting their electricity needs. Okay.
I think my estimate is only 10 kilowatt hour. That's somewhere. I think it's basically 100 terawatt hour divided by 10 billion. That come out.
That's right.
10 kilowatt. Yeah.
Per person. Yes.
Yeah.
Per person. You're right. Yeah, and and that does not include the EV needs, which this is just for electricity, right? So, yeah. And the way it'll work is, so I put 2 zeros on the numbers just to make it easier to remember, but the way it'll work is that the cheaper the batteries, the more of it we'll use, and the more expensive, the less of it we'll use. Okay? So, but that is the way we got to there is to estimate the U.S. and then multiply by 10 to get to the entire world. Yeah.
And the fact that you showed there is probably enough lithium resource, but we need to really catch up on the speed. That's really a key message here, I think.
Yeah. So production scaling is really the showstopper, I think.
Yeah. Okay. Thank you, Yet, for that very inspiring talk.
Thank you all.
Okay. I think we're done with the